Hello everyone, welcome to the 8th module of this course, which is a short module on ferroelectric FETs. The disclaimers remain the same.
So what exactly are ferroelectric ramps? So ferroelectric ramps were actually the first memories that were commercialized apart from the static RAM or the dynamic RAM. So the existence of these ferroelectric properties or the ferroelectric ramps was explained way back in 1951 itself. And in 1955, the first memory demonstration was also complete. So this is one of the earliest memories that was actually proposed. And at that time, people used to call it a dream memory that had very fast switching times, like 50 nanoseconds or something. And the endurance was one of the key factors that propelled the development of these kind of memories. So the endurance greater than 10 per 13 cycles was already observed, and it could work with the logic voltages. I mean, your NAND flash and all, they require very huge amount of voltage, right, for programming and arrays. But these ferroelectric ramps, they could work with logic voltages, and that is what propelled their development. And also they were low power consuming, because here the programming and arrays is not by injecting some electrons somewhere, but it's because of changing of polarization. So they could be used for very low power applications. So RFID was one of the first application where ferroelectric ramps were used. And by 1980s or something, many of the industries, many of the startups in US actually started coming up with commercial ferroelectric ramps. So these were kind of the memories which were much more mature than the NAND flash technology. And what makes these ferroelectric ramps very, I would say, what is essentially a ferroelectric material? So ferroelectric material is something which is piezoelectric. I guess you all must be aware about piezoelectric materials. You apply force on it, it will generate some amount of electricity, or I would say some amount of potential. EMF develops across that piezoelectric material the moment you apply any stress or strain on it. And why does that happen? So all ferroelectric materials are basically piezoelectric. You put pressure on them, you will generate an EMF. At the same time, they're non-centrosymmetric structure. So what I mean by non-centrosymmetric structure is that in a symmetric structure, so let's take the case of this PZT, which is the most common kind of ferroelectric material, perovskite based ferroelectric material, which was used at that time. So here, what happens is, at the center, you can see that the center position is not occupied by any atom. So there are two stable positions that Ti ion, or zirconium, titanium or zirconium ion can kind of occupy. So this is one stable state. This is the other stable state. There's no stable state in the center. Since there are two stable states and none of them is at center, we call this structure a non-centrosymmetric structure. And what is the property of centrosymmetric structure? If it were in the middle, then the effective polarization or the effective dipole moments will cancel out each other from the top and bottom. And as such, the net dipole moment of this would be zero, or the net polarization would be zero if it were a centrosymmetric structure. But here, since charged kind of ion is close to some low, I would say it is either close to this part or close to this part. So effectively, dipole moments do not cancel out each other, and there is an inherent non-zero polarization. And this polarization value is actually huge. So effective charge is given by epsilon times E plus polarization value. And polarization is so large in these materials that it actually dictates its kind of charge in nascent state, or when you don't apply any electric field. And what's the best part about it? So as I told, that titanium or zirconium occupy either of these stable positions, and you can actually change their location by applying an electric field across this material. So you can change effectively the net dipole moment, the effective configuration of those dipole moments, and hence the net polarization. So the polarization of these ferroelectric materials can be changed from one state to another just by displacement of this atom. I mean, this is what is happening at the atomic scale. But what you observe when you apply an electric field across this material is, you observe that it shows two different levels of polarization. And that is inherently because of this displacement of atoms. So this is the typical polarization versus electric field or versus voltage curve that you measure for any ferroelectric material. So let me explain that. So you have two distinct polarization state. And what are those two distinct polarization state? If you do not apply any electric field, you have these two different polarization states. So at zero electric field or at 0 volts, whatever polarization you have across the ferroelectric material that is called remnant polarization. So there are two values of remnant polarization, one which is corresponding to the first state, other one which is corresponding to the second state. And how this works is, you apply a voltage, you apply electric field, then what happens? It remains at its PR value. I mean, it remains close to the PR value. This is kind of a non-ideal kind of characteristics, or the experimentally observed characteristic. What ideally, or what P kind, the P curves that you draw for ideal ferroelectric cap would look something like this. It will remain at PR till this critical voltage is achieved, which is also known as the critical coercive voltage, or the coercive electric field. And after that, the polarization suddenly switches to this level, which is called PSAT, or the saturation polarization. Here it's from a practical device, so you don't have a smooth, or I would say a constant PR value till EC and then a sudden rise, but you have a gradual rise. Even then, let me explain what exactly is happening here. So if you apply a positive voltage, you kind of apply a positive electric field. As the voltage reaches a critical value, which is called a coercive voltage, which generates a coercive electric field, which is the critical electric field, what happens? The polarization switches from this value to the positive saturation value. So this value of polarization is called saturation value. Why it's called saturation? Because it kind of saturates at this value. Here it's not saturating well, because it's kind of a non-ideal kind of a capacitor, ferroelectric capacitor. But in ideal ferroelectric materials, what happens is, the moment it hits this critical voltage or this coercive voltage, the polarization changes, it switches to the other state, and it kind of saturates at this value. Even if you increase the voltage or field after this, it will remain at that value. It won't change much. And then if you kind of reverse the direction, then you hit that polarization, remnant polarization state, that is the other state. And then if you continue to reduce the voltage, or if you continue to go for negative voltage, reverse the electric field across this, again you will hit a coercive voltage. And at that voltage, what will happen? Suddenly the polarization will switch to the other state. So this is basically how you understand this PE curve. So there are three major components that you can obtain via this PE curve. One is this remnant polarization, second is this saturation polarization, and third is this coercive voltage or coercive electric field. And the best part about ferroelectric materials is that most of these ferroelectric films are polycrystalline with domains. Now, polycrystalline, you know that in polycrystalline material, you have several kind of monocrystalline, or I would say, what is polycrystalline material? So you have single crystal kind of things. I mean, you have single crystals separated by grain boundaries. So those single crystal things are called domains here. So what exactly is a domain? Domain is a local range of 100 nanometer, which has one fixed polarization state. So in a particular domain, you have either this remnant polarization or this remnant polarization, and they are separated by grain boundaries, since it is a polycrystalline material, right? So different domains have different polarization. So you can have a positive, you can have a plus PR situated immediately in the neighborhood of a minus PR domain. So that is how you have a kind of mixed kind of polarization kind of distribution within this ferroelectric material. And what is the biggest concern? If someone asks you what is the biggest concern with ferroelectric ramps or ferroelectric materials, so switching speed is a major concern. It's not a major concern for PZT or perovskite based or BTO or perovskite based ferroelectric materials, because they show some nanosecond level switching, 50 nanoseconds or something. But if you talk about doped HFOX, which are CMOS compatible, their switching speed is only some megahertz, while we want to operate at frequencies which are some gigahertz, right? We want to operate with as low pulse width as possible, close to some nanoseconds. So if you want to work with doped HFOX, which are CMOS compatible, then you can't work at that speed. So that is one of the major hindrance, or I would say major challenge, which is hindering its development, hindering ferroelectric ramp development. However, people have actually come up with several stacks, and you can see a lot of ferroelectric ramps in the future. Going into the future, ferroelectric ramps are definitely going to be popular. Now let me talk about this polarization switching. So what exactly happens during a polarization switching? So what exactly happens is, let's say the dipole moments are like this. It's plus minus, plus minus, plus minus. But somehow here there is a domain where there is this polarization reversal. So here instead of minus, you have this plus. Here also instead of minus, you have this plus. Here also instead of plus, you have this minus. So these are few domains which are showing kind of a net polarization or net dipole moment, or a state, polarization state, which is different than its neighborhood, right? So this is where the nucleation starts to happen, and only nucleation domains larger than a critical size are stable, similar to the PCM devices. So you saw there itself that thermodynamics plays a major role in this. Even for ferroelectric materials, ferroelectric films, thermodynamics plays a major role, and only nucleation domains larger than a critical size are stable. So first, you'll have these nucleation sites. So what could be the possible reason for these nucleation sites? It could be just because of the polycrystalline nature, or it can also be because of defects or traps or existing charges within the ferroelectric film. So after that, what happens? You apply some electric field across it, and then what happens is domain propagation happens. So what happens is these domains tend to flip the neighboring domains. These domains tend to flip the neighboring domains, and because of that, there's a polarization reversal, and it kind of propagates along this direction, along the direction of the electric field. And now what happens is the moment this polarization, like this domain propagation happens, after that you'll have something like this. You'll have a situation where there are these kind of domains which are way different as compared, which are having dipole moment, which is way different as compared to the existing polarization of the entire material, or the dominant polarization of the entire material. And after that, if you continue to apply the electric field, what happens is these domains kind of expand in the lateral direction, and finally you have this domain reversal or kind of polarization switching. So what are these ferroelectric materials, or what are these popular ferroelectric materials? So Rochelle salt, I guess you must have heard its name in chemistry, in class 11th chemistry, I guess. So Rochelle salt, people knew that Rochelle salt like shows this kind of a PE curve, which is having a saturation kind of thing, and having two different remnant polarization states. They found it way back in 15th century, just imagine. And Debye also explained this theory of ferroelectric polarization at that time itself. Even though this field was kind of ignored, but during World War II, people were very busy developing new materials and all, and then somehow they came up with this PZT, BTO. I mean, PZT is nothing but a perovskite. BTO is also a perovskite. These were found during World War II, and when they characterized them, they found that in 1940s actually, and when they characterized it, they found that they had very high PR. They had a very high remnant polarization value. However, their dielectric constant was close to 1000. So if something's dielectric constant is very high, can you use it as a gate dielectric? Think about it once. So won't your gate capacitance increase significantly? And the moment your gate capacitance increases, your speed, or the speed with which you can operate with that kind of capacitor, that also reduces. Anyways, so you think about this once. And also these materials are not CMOS compatible. So none of the CMOS industries, or none of the industries, would actually like to go ahead with these kind of ferroelectric materials. So till now, I mean, although standalone memories based on PZT were realized, like I talked about 1980s, those startups, so those were mainly using PZT memories. However, in FET kind of architecture or something, this PZT cannot be used because they are non-CMOS compatible. So as I told, they are not CMOS compatible. So recently, this field again gained attention. Why? Because of this development of impurity-based HFOX. So if HFOX or HFO2, which is kind of a high K dielectric, which is usually used in your MOSFET, is doped with yttrium or silicon or even zirconium, HZRO, which is called HZRO, then it shows some amount of ferroelectricity. So you obtain that PE curve. But how that PE curve compares to this PZT or something? So those PE curves have a low remnant polarization. They have a higher value of coercive voltage, but at the same time they show low dielectric constant. So the dielectric constant that even HZO or zirconium doped HFOX shows you is close to 22. So you can actually work with that. You can actually make even FETs with that. So that is kind of the advantage of it. Another advantage is that since this HFOX is already being used as the high K gate stack in high K gate stacks, and silicon or zirconium is kind of readily CMOS compatible, so you can actually dope HFOX and then use it and make it CMOS compatible. The other problem with this kind of ferroelectric ramps is that ferroelectric materials are deposited typically at temperature greater than 450. And I told that the moment you hit this 450 kind of a ceiling, you cannot use it after deposition of your FEOL. So it can't be used for back end of line. So above this back end of line, I mean above interconnects, you cannot integrate it. So it has to be integrated between this front end of line and the back end of line. So this is one constraint while designing this ferroelectric ramps. It cannot be integrated in the back end of line or above just interconnects. So initially, the memories that I was discussing about that those startups in 1980s came up with were basically using PZT, and they were using this PZT or the ferroelectric material in the form of a capacitor, and they were using it. The operation was similar to the DRAM, 1T 1C DRAM. So they were also using this instead of capacitor, they were using this ferroelectric material as the capacitor. So it was similar to the 1T 1C DRAM, or they were also using 2T 2C form. So 2T 2C form basically consists of two complementary data storage. So one of the capacitor is storing 1, the other one is storing 0, and the combination 1 0 or 0 1 is deciding your effective logic value which is being stored. So if the combination is 0 1, let us say we are encoding a 1 via that. If the combination is 1 0, then we are encoding the memory state 0 via that. So it was something like that. And why was it used? Because readout of 1T 1C is a big problem. So let me discuss that. So sense margin for this 1T 1C was very low. Why the sense margin was very low? Because they were purely relying upon the polarization charges, charge sharing between the 1T, like charge sharing between the bitline capacitance and this ferroelectric capacitance. So ferroelectric capacitance in the case when it is completely discharged, and in the case when it is polarized. So in those two cases, there was a difference in the charge that it could share, and that charge was stored on a floating node, which was kind of the bitline, and then they just sense that bitline voltage. So if you're relying on charges on any floating node, then definitely your sense margins would be very low, and that is what was happening here. However, that is why they did not gain much popularity. But FRAMs were also being used in NVSRAMs at that time. So NVSRAMs, when people conceptualized this, FRAMs were the first candidates that people kind of came up with. However, the problem with FRAMs again there was that they were not CMOS compatible. So they could not be integrated in the same process as they were integrating your SRAMs using 16. So that was one problem there. And yeah, because of these problems in readout, which I already told, that you are sensing kind of charges on a floating node, which will not give you a very high sense margin. So because of that, the sense margins were low, and people, instead of going ahead with sensing, the charges at any floating node, they started to go ahead with designing FEFETs. But from 1980s to 2010s, that is for nearly these 30 years, FEFETs cannot be manufactured. Why? Because all the ferroelectric materials that we knew of, they were not CMOS compatible. It was only, after this HFOX, like doped HFOX was discovered, that people started again, thinking about FEFETs and realizing that. So what are FEFETs? So as I told you that in 1T, one ferroelectric caps, the data is stored as, charges on floating BL node, and sense margin is really small. So instead of that, people conceptualized this idea of ferroelectric FET, where they told that, okay, instead of sensing this charge, what we would sense is, we would sense the current. And also the presence of noise kind of increases the readout problems if your sense margin is small. That is true for even SRAM. I mean, this thing is true for any device. If your sense margin is small and if there's a huge noise, then definitely your readout problems will increase. So in FEFETs, what they actually rely upon, they sense the drain current instead of the charges on the floating nodes. And drain current is actually something which can be easily sensed, or which will give you a higher sense margin. So what effectively happens here is, they integrate this ferroelectric material in the gate dielectric or the gate stack. So it is available in two configurations. The first one is called MFIS configuration, metal, ferroelectric, insulator, and semiconductor. Second one is called metal, ferroelectric, metal, insulator, and then semiconductor. So in these two configurations of ferroelectric FETs, you integrate this ferroelectric material within the gate stack, and this polarization effectively is charge, right? So the charge on the gate stack, if there is any charge on the gate stack, you are kind of modulating the threshold voltage. So just by switching this polarization state of this ferroelectric material, you are inducing two different threshold voltages. If you're talking about extreme values of those polarization. However, if it is polycrystalline, and if there are different domains with different polarization states, then by applying appropriate voltage values, you can switch those domains one by one. And if you are able to do that, you can also achieve analog kind of threshold voltage states, where you have different threshold voltage states in the same device. So I'll also discuss about that in the last slide of this lecture. So this is all about MFIS and MFMIS structure. And there is yet another form of ferroelectric memory, which is called FTJ, or ferroelectric tunnel junction. So in that, this ferroelectric material is used as a tunneling junction between two different, like it acts as the tunneling junction. And the tunneling current actually depends upon the direction of polarization of this ferroelectric material. So using or sensing that tunneling current also, you can actually judge the direction of polarization. So here in FTJ, you are sensing the tunneling current. In your ferroelectric FETs, you are sensing the drain current or the threshold voltage value. And in your 1T1 ferroelectric cap based kind of DRAM kind of structure, you are actually sensing the charges on the floating BL node. So in terms of sensing, FE FETs are the best. Even FTJs have like readout problems. So, and anyways, I just wanted to give you a brief overview of what exactly are these memories. So there are also some problems with these ferroelectric FETs, which you encounter when you use them. So what are those problems? So first is depolarization. So what happens is, along with aging, they develop some amount of charges. And once charges develop in the ferroelectric layer, what happens is it reduces your remnant polarization. So here you can see that when these charges kind of accumulate inside your ferroelectric material, what happens is the PR value reduces. So the PR value reduces, but if you increase the electric field, what will happen? It will again reach this PSAT. So this is the PSAT value. This is the PR value. So if you increase the electric field, it will reach this PSAT. Even in that case, only the PR kind of shrinks. Only the PR shrinks due to depolarization or development of charges inside the ferroelectric layer. There's also one property which is called imprint. So what imprint leads to is, it leads to a shift in the threshold. It leads to a shift in the PE curve, or it leads to a shift of the coercive field basically. So this is also one of the problems which people encounter while handling these ferroelectric caps. And the last but not the least, we have this fatigue. So fatigue is the mechanism which kind of denotes endurance failure. So what happens is, if you cycle it continuously for several cycles, what happens is your PE shrinks. I mean, this kind of shrinks throughout. I told that when there is this depolarization, only PR changes. The curve will still go to this PSAT value. However, in the other case, that is this fatigue, which happens due to endurance failure. I mean, when you are switching this device back and forth between the two polarization states, this entire PE curve shrinks, and your PSAT also shrinks in that case. So that is the difference between fatigue state and depolarization. So just by comparing, the virgin kind of PE curve with the PE curve after a few cycles, you can find out what is the dominant mechanism. Is it imprint, or it is depolarization, or it is the fatigue, which is leading to reduction in your performance of your ferroelectric material or ferroelectric cap. So the last topic which I would like to touch upon is how these ferroelectric FETs can be used as synapses, or how can these ferroelectric FETs be used for neuromorphic computing. That is what we are more interested in, right? So what we do for using them in neuromorphic computing as synapses, we apply pulses greater than coercive field. So I told that these ferroelectric materials have kind of polycrystalline structure, and different domains have different polarization. So let's say this is the ferroelectric material, and these are different domains having different polarization. So here the polarization is pointing towards this, or the dipole moment is pointing towards this. It is again pointing in the reverse direction, then again from bottom to top, then again from top to bottom, and so on. So if you apply one pulse greater than the coercive field, what it will do? It will switch some of those domains. So let's say you read the device state. After that, you do a IDVG sweep. You obtain something like this. You obtain this characteristics. Now, if you apply two pulses, two similar pulses, what happens is you switch some other domain as well. For instance, here, when you applied one pulse, only one domain switched. Now, if you applied two pulses, what happens? One more domain switched. So here you can see that this domain switched. So if the domain switches, the effective charge on the oxide layer that changes, and that shifts the threshold voltage. Now, if you again apply a pulse, what will happen? Some more domain will switch. So here this domain switched. So now what happened? You again kind of tempered the charge on this gate stack, and the moment you change this charge on the gate stack, what happens? Your threshold voltage again shifts. So If you continue to apply identical pulses, you will continue to switch few of those domains until you switch it entirely, until you achieve polarization switching. So the moment you do that, the threshold voltage cannot be reduced beyond that. So this is how you can achieve analog threshold voltage states with your ferroelectric FETs. And the moment you talk about analog threshold voltage states, you talk about analog weights, analog conductance states, or threshold voltage state. And by that, you kind of realize the synapse. So this is all about ferroelectric FETs that I thought that you guys should know. Another very interesting component on concept which comes with ferroelectric materials is the concept of negative capacitance that I could not discuss because of timing constraints. I had to keep this lecture short so that you can at least go through it before the discussion session. I know it's very difficult, and I was pretty busy with these hospital arrangements and this COVID care, coordinating with the health center and all. So I could not upload this lecture yesterday. Extremely sorry for that. And this is going to be the last lecture. So best of luck for your future. And yeah, make sure that you attend the discussion session tomorrow.